Well, good morning, everyone, and welcome to the Geothermal Exchange Organization webinar. We're happy that you could take the time from your busy day to join us this morning. My name is Ted Clutter. I manage outreach and communications for GEO, and I'll be your moderator for the webinar. Our topic today is geothermal heat pumps versus variable refrigerant flow systems, and it's a presentation of recent scientific research sponsored by GEO, and that's at the American Society of Heating, Refrigeration, and Air Conditioning Engineers, ASHRAE, International Headquarters Building in Atlanta, Georgia. For your friends and colleagues who could not attend today, and for your review after the webinar, our presentations are being recorded and will be available on the GEO website. There is a questions pane on the right-hand side of your screens. I'm sure all of you can see it. You can type your questions there for our Q&A session at the end of our keynote presentation today. Our presenters today are Doug Dougherty, President of the Geothermal Exchange Organization, and Dr. Jeffrey Spittler, Regents Professor of Mechanical Engineering, Oklahoma State University. He'll be accompanied by his research team, which includes Laura Southard with Oklahoma State University, and Dr. Xiaobing Liu of Oak Ridge National Laboratory. First up is Doug Dougherty, as I said, President and CEO of GEO. He's an expert in advocacy and management. He's been president of GEO for 4 years, coming to the position with a master's degree in public policy and long experience in government and regulatory affairs for the state of Illinois. In the 1980s, he managed the geothermal heat pump marketing program for a public utility, essentially jump-starting the industry in the state. He came to GEO following a 14-year stint as president of the Illinois Telecommunications Association. Doug?
Thank you, Ted. Good morning to everyone. Just a brief overview of the Geothermal Exchange Organization. We are the national trade association representing the geothermal heat pump industry, and we really have 5 areas of focus: advocacy, outreach, partnerships, standards, and research. We have objectives to create sensible public policy, have common interests with allies, public relations and outreach for the industry and issues research, and quality training and certification. And the focus of today's webinar is research, and specifically a research project of the ASHRAE headquarters building in Atlanta, Georgia. So the ASHRAE headquarters building in Atlanta, we knew it was going to be what's termed a perfect living lab when the headquarters building was rehabilitated in 2006 and 2007. And part of the rehabilitation was to install HVAC systems that could provide data on energy usage and performance. And good data were provided, but not at a level of detail to do a scientific comparison of the 2 heating and cooling systems. So we embarked on a research project to compare the 2 operating systems at the headquarters. ASHRAE provided data for this study, but the organization does not endorse, recommend, or certify any equipment or service used at the ASHRAE International Headquarters. As I said, GEO funded the research project, but we did receive some financial support from Southern Company. And we would like to thank Southern Company for their lending their services of a power engineer to assist with on-site measurements. Shown in this picture are Keith Swilly on the left and Chris Gray. Both were instrumental in getting Southern Company's support for this valuable research project. And now I'd like to introduce our main presenter today, Dr. Jeffrey Spittler. Jeff Spittler is a Regents Professor of Mechanical Engineering at Oklahoma State University, where he holds the OG&E Engineering Technology Chair. He is a past president and fellow of the International Building Performance Simulation Association and a fellow of ASHRAE. Products of his ground source heat pump system research include a design tool for ground heat exchangers, methods for estimating ground thermal properties, and simulation models implemented in eQuest, Energy Plus, and other programs. This academic year, he is on sabbatical and serving as the Fulbright Distinguished Chair of Alternative Energy Technology at Chalmers University of Technology in Gothenburg, Sweden. It's my pleasure to introduce Dr. Jeffrey Spittler for his presentation.
Well, good morning, everyone. Welcome to our webinar. As Doug, and thank you, Doug and Ted. As Doug mentioned, I'll be discussing the ASHRAE headquarters system and our evaluation of it. And first, I'd like to introduce the project team. That's me on the left. Xiaobing Liu at Oak Ridge National Lab actively participated in helping us analyze the data. And Laura Southard was at the time a graduate student at Oklahoma State University, and this was the subject of her master's thesis, which means that she really did all the hard work on the project, did all the data analysis, and is sort of largely responsible for what we're going to hear about today. Okay, well, it is the ASHRAE headquarters building. A couple of photos of it. This part here is the part that was added in the 2007-2008 renovation. This is the Learning Center part here, and then from over right here to the left, that's the original building that was built in the 1960s. The building's won, since being renovated, a number of awards. It's a LEED Platinum building. It's Energy Star rated, and it has an ASHRAE BEQ of A- or very good. But we're primarily interested in the fact that since it was intended to be a living laboratory, there are, I think there's around 1,600 measurement points altogether. We used quite a few of them, but not all of them. When it was renovated, one of the things that was done was that the office space was made open plan, so it allows for more daylighting, but also that open plan nature of it has some impact on how the systems perform, which we'll discuss later. So it's got three systems. The ground source heat pump system serving the second floor, variable refrigerant flow system serving the first floor, and then a dedicated outdoor air system that serves both floors with fresh air. And the first floor is shown here. I'm sorry about the small view here. I don't expect you to read the blueprint today, but there's a total of 17,213 square feet that are served by the VRF system, actually by two VRF systems that are measured or metered. Now there is also two other VRF units that serve the computer server room, this rectangle here, and also the front foyer area. And then this rear staircase area is actually served by a ground source heat pump unit. So the VRF system serves almost all of the first floor, but not quite all of it. It includes office space, there's a mail room, and then also the learning center, which is, you could call it classroom/meeting space. It's got two outdoor heat recovery units. They're 14 tons each. Here's one of the units on the roof here, and if you see this white piping here, this is insulated refrigerant piping serving the individual fan coil units, the inside units, and there's 22 of those. Okay, one important feature of the VRF system that's very important to understand for the comparison study is that the VRF system has a single set point temperature. Okay, so each unit is attempting to maintain a specific temperature. Now the temperature is set by the building energy management system, but occupants of the building can reset the thermostats. They can do this for both the ground source heat pump system and the VRF system, but they have with a ±3 degree Fahrenheit latitude to make it cooler or hotter. But with whatever the final set point is, the system tries to maintain that within ±1 degree Fahrenheit. So individual fan coil units, they don't switch back and forth between heating and cooling like you might expect. There's some algorithm. I don't know exactly how it works, but what we've from the measurements, from the data, the units don't switch back and forth. But in this open plan office space, and this is some of it here, we do often find that adjacent units or units serving adjacent spaces are running in opposite modes. So there's a fair amount of time when you'll have some units in heating mode and some units serving adjacent zones in cooling mode, and that's part of the story of our research project in terms of why the outcome is the way it is. Okay, on the second floor, we've got the ground source heat pump system. Most of the units, heat pump units, are up in plenum spaces, but there are a few console units. It serves the entire second floor plus the rear stairwell, so it's a little bit less floor area, 15,558 square feet. It's mostly office space, and there are a couple of conference rooms. This is, by the way, the pump closet here. It's got a glass door on it, so visitors to the building can see it. The ground source heat pump system has 12 boreholes. They're each 400 feet deep. And there's 14 water-to-air heat pumps. Total nominal capacity 31.5 tons. The heat pumps are two-stage, and they have variable speed ECM fan motors. So in fact, they run at 3 specific speeds. There's a speed that when the heat pump's off, but the building's occupied, it runs to circulate ventilation air. That's the lowest speed, and then when it comes into the first stage of cooling or heating, there's an intermediate speed, and then when it comes into the second stage, it runs at high speed. So this ground source heat pump system has a different control strategy, or different control system. So there are separate heating and cooling set points, not one set point like the VRF system. And this typical value set by the building energy management system is 68 for heating, 74 for cooling, but users can reset the thermostats up and down within 3 degrees. And again, they're two-stage heat pumps, so when the temperature gets more than a certain level above the final set point, it goes into low-stage cooling, and then when it goes higher, it gets into high-stage cooling. Okay, there's also a dedicated outdoor air system, a DOAS system. And it provides what I'm calling partly conditioned outdoor air to both floors. So let's say the air coming in is always lower than the room temperature. In the summer, or when it's warm outside, it's actually controlled to be 55 Fahrenheit. But when in the winter, when it's cold outside, it's possible that the air temperature could drop below that, but it actually stays very close to 55. So we're providing this cooled air that's always lower than the room temperature, so it's sometimes over cool spaces in shoulder season or in the winter, and it has the effect of, as far as the ground source heat pump system and the variable refrigerant flow system goes, it increases the heating loads on those units and decreases the cooling loads. Okay, and this is the DOAS system on the roof of the building. This is the part of the system with the fans and the air and the enthalpy wheels, and then the cooling is provided by these these are condenser units that are staged. They look much like residential, I don't know, 5-ton units or something. I don't remember the exact capacity, but those are staged, and that's what actually provides the cooling for the DOAS. Okay, later in the presentation, we're going to talk about the loads themselves that were measured. But right here, I'd like to talk about the loads from a qualitative standpoint. Talking to different people who know bits and pieces of how the building works. I've heard various things like, oh, the occupancy is a lot different. So on. So let me just tell you what we know about it. First of all, the lighting and the plug loads, those are actually measured for the metered spaces, and they are almost exactly the same. So I don't have the numbers on the tip of my tongue, but if you wrote them as, say, 2.0 watts per square foot, they would appear to be the same for first and second floor, and that's true for both lighting and plug loads. So they're within a few percent of each other. They're very close. Now, occupancy, there's no occupancy meter per se. What we have available are, first of all, we have the ASHRAE phone directory. You know where people are stationed. So that's what I'm calling normal occupancy. So the first floor, there are about 400 square foot per person. And the second floor, there are 259 square foot per person. So the actual density is higher on the second floor. By a fair amount. So one person per 259 square foot instead of one person per 400 square foot. But then the first floor also has a learning center. And we don't have occupancy records for how many people are using the learning center. I was there once for a meeting on Saturday, and I think there were about 50 people in the room. Okay, but what we do have is a schedule for the learning center. It's used about 26 hours a month. And so that's going to increase the density on the first floor. You know, we don't know exactly, but you know, if I had to guess, I would guess that the actual effect is somewhat similar, but it might be higher on first floor or higher on second floor, but it shouldn't be that much difference. A fairly important difference between the spaces, though, is that the first floor has considerably more airflow than the second floor from the DOAS system. So its average is 2560, and it's fairly constant throughout the year. It doesn't swing up and down. And on the first floor, the second floor is 1480 CFM. So you could say that the second floor has about 60% of the airflow that the first floor has. Now, the effect of the DOAS is actually, as I mentioned, it increases the heating loads and decreases the cooling loads. So we expect that the heating loads on the first floor are maybe higher than they would be because of the high DOAS airflow rate, and on the second floor, the heating loads may not be as high. Cooling, and on by the same token, right, there's more sort of free cooling, as it were, for the provided to the VRF system on the first floor. It's not free because it's provided by the DOAS system, but it's going to decrease the cooling loads on the first floor compared to the second floor. Okay, now there's some other features, right? The rooms on the second floor, well, they have heat gains and losses from the roof. The first floor has more glass facade, but part of this is conditioned by the non-metered VRF system. So, the envelopes on the two floors aren't exactly the same. But as a result of the DOAS system and the envelope, the first floor has higher heating loads, the second floor has higher cooling loads, but overall the building has much higher cooling loads and heating loads. So we'll look at the actual numbers a little bit later. And I forgot to mention when I started, but we're going to take a couple very short breaks, and Ted's going to make an announcement now, and then I'll come back in a minute.
Well, thanks, Jeff. Again, this is your moderator, Ted Clutter. I've got a quick note to those who may be tuning into our webinar a little late. A reminder that a recording of the webinar will be available on the GEO website shortly after this event, and we will have a brief Q&A period following this presentation where I will read questions for answers by Dr. Spittler and his team. Thanks, Jeff.
Okay, thanks, Ted. Thanks for also giving me a chance to get a drink. So, okay, we're now going to start the results discussion, and I've got this broken up into, first of all, discussion just of the energy consumption and what we're able to determine without looking at the heating and cooling loads. Then we'll move on to discuss the heating and cooling provided by each system and also the system performance in terms of COP and EER. And throughout the results discussion, I've got some slides that start with why, where I can provide a little bit more information besides this are the results. That's when I'll do it. Okay, so if we start with the total monthly energy use for the building, you can see that it's here in kilowatt hours, and this includes all three systems, so the ground source heat pump in blue, the VRF in red, and then the DOAS in green. A couple of things you might notice from this. First of all, the DOAS uses a lot of energy. Right? It's also providing a fair amount of cooling for the building, so you can see fairly high energy usage in the summer months, lower usage in the winter. And also the building loads peak in the summer. As pretty much as you would expect for Atlanta, but you can see it confirmed here. By the way, the first part of our study here is in our study period that we started with was July 2011 to June 2013. So you see 2 years of data starting in July. And there's a reason for that, which has to do with the fact that earlier than that there were some large large gaps in the data where there might be a few weeks missing, that kind of thing. So when we looked at the data, we decided these 2 years had a very complete data set and made a good period to analyze the system for. Okay, now if we look at energy usage just for the ground source heat pump and the VRF system, that's what we're comparing. If we look at it per square foot, what we have here is a plot for every month, so starting in July 2011, the kilowatt hours per square foot used by each system. And a couple things here. First of all, you see that the VRF in most months is using more energy, often considerably more. But in the summer, like say July 2012, August 2012, September 2011, in those months the two are, they're fairly comparable. The VRF is using more, but not all that much more. But then in the shoulder seasons and in the winter, it's using considerably more energy. If you look here, there is 1 month in July 2011 when the ground source heat pump system is using more energy than the VRF. Other than that, the VRF is using more. So, interesting way to look at it, but maybe even more interesting way to look at it is to plot the power consumption during occupied hours versus the outdoor air temperature. So we took the data, now this is watts per square foot instead of kilowatt hours per square foot, because we're just taking the average power versus the outdoor air temperature. And we divided it all into bins. And you see there's 3 sets here. So this is the VRF here, the red, like that. And then the DOAS, right? And once the temperature gets below about 55, it's very constant. That's because it's only running the fans and the enthalpy wheel in those conditions. And for the ground source heat pump from the VRF system, these black lines are what is called a change point model. It's a way of characterizing energy consumption. So, as you'd expect, when it gets hot outside, the building loads are going up. So, of course, we're going to use more power. Right? That's true for all 3 systems. They're all increasing as temperature gets higher. And also for the VRF system, we expect that the efficiency is going to be impaired some as the temperature gets hotter. So that may explain some of the increase. With the ground source heat pump system, the temperature it's indirectly correlated. So, yes, when there's a higher load, the ground loop temperature will be higher. It's not as direct, and the temperatures are more uniform. So, we could look at this, and we spend a lot of time staring at these plots. There are some interesting features, like when it gets really cold, the VRF system is using about 3 times as much power at really low temperatures. But we'll skip to the next slide for a second. If you look at the actual temperatures, right? I went and did, I think last week, did a histogram of the temperatures in this 2-year period. These are, the number of hours for each bin. And what you find is, well, at 15 degrees Fahrenheit, there's very few hours. So, in a sense, it's not too relevant that the VRF system uses so much more than the ground source heat pump system at 15 degrees Fahrenheit, because there's just not that many hours. But there's lots and lots of hours in sort of this middle range. I guess you could characterize it any way you want in terms of what percentage fits in what range, but you see there's lots of hours, in the 50, 60, 70 degree range. And in that range, we see a really large difference between the systems. It's not so large, it's not as large as here in terms of watts per square foot, but in terms of the ratio, the VRF system in this range is using about 3 times the energy of the ground source heat pump system. So that's an important, it's a very important part of the energy consumption picture. It's one of the reasons why in the shoulder seasons the VRF energy consumption is so much higher. And as it gets warmer, well, then they get closer together and the difference isn't so great. Okay, so we'll look at a lot of the results in slightly different ways. This is also a binned analysis. So again, it tells us at any temperature how much energy the VRF system is using in terms of the average use during occupied hours for watts per square foot. One thing we've done differently, though, is here we're showing we've divided the energy into how much is being used for heating and how much is being used for cooling. And one thing that strikes me when I look at this plot is that when you look at, say, temperatures like 50 degrees Fahrenheit, you see there's quite a bit of energy being used for heating and quite a bit being used for cooling. And in the next slide, on the very same scale, we'll flip to the ground source heat pump system. And you can see there at 50 degrees Fahrenheit, there's hardly any energy being used for heating, and there's some energy being used for cooling. And also, if you can see this here, we have these green bars, and they're what we're calling unallocated. What does it mean? Well, unallocated means that all of the heat pumps are off, and so the system's not actively providing any heating or cooling. All the compressors are off, but the fans are running. The pump may or may not be off, but the ground source heat pumps have individual control boards that are using something like 10 or 15 watts each, and so that's consuming a little bit of electricity. So in other words, the ground source heat pump has at least some hours over this range when all the heat pumps, all the compressors are off. If you go back to the VRF system, you see there's no hours for unallocated that are shown. That's because I think we found in 2 years that there was maybe 1 hour when none of the VRF systems were running, providing heating or cooling. Another way of saying this is that the VRF systems, all the units run all the time, almost. And they seem to spend a fair amount of time heating in one space and cooling in the next space. And that's part of the explanation for why it's using so much energy. It's simply that, we think, simply that you've got all the compressors running, and they're providing both heating and cooling, and they're using energy. Okay. Another way to look at it, what we tried to do was to find hours. We filtered the data to find hours when, for example, all of the ground source heat pumps were only cooling, or all of the VRF units were only cooling. Right, and to some degree, this tells some of the story. If you note, if you compare this to the earlier slide, the curves, as they were, they're a little bit closer together, right? And that's because there's no heating going on in the VRF system, so the power consumption is a little bit lower per square foot. And if you look at hours when there's only heating, you can compare with these two plots. You can compare the system performance without the simultaneous heating and cooling. Get some idea. The VRF system looks a little bit better compared to the ground source heat pump here, but still the performance, even when it's heating only, it's not as good. And so there are other things besides this simultaneous heating and cooling going on. Okay, so I have a kind of a more detailed illustration of what's happening. I picked a moderate day, April 3rd, 2013. It's a day in Atlanta when the morning low was 43. Afternoon high was 63. So, probably a relatively moderate day. There shouldn't be too much heating needed, shouldn't be too much cooling needed. So let's look at what happens with the two systems on that day. So this is the power usage for the two systems. Again, watts per square foot, just the instantaneous power measurement. You can see at night, the ground source heat pump system, again, is shown in blue, VRF in red. Very little energy consumption at night, but in the day, about 5:30 in the morning or so, both systems come on, and the VRF system ramps up quickly. Ramps up quickly partly because I think all the units are on, all the compressors are running. The ground source heat pump system has only a few units coming on. And, throughout the day, units kick on and off. You can see the sort of discrete changes in the number of ground source heat pump systems on. The VRF system also has spikes that are somewhat larger. And in any case, if you look at the overall power consumption, it's maybe 4 times as high. Certainly, I didn't figure it up for the day exactly, but say somewhere between 3 and 4 times as high for the VRF system. So if we look at the temperatures, we plotted the ground source heat pump zones, their temperatures during the day. You see they start between about 70 and 73.5, and over the day they climb up, and they, the hottest ones are about 75, and the coolest ones, just under 73. For the VRF system, we divided it up into 2 plots, and the reason for this is there's about a third of the units, I think, are cooling, and they're cooling all day long. Again, they're not switching back and forth between cooling and heating. They're running somewhere, the lowest ones are running under 71 degrees, and the warmest one, it's hitting 75. That particular zone, the zone next to it was heating. That may explain some of the temperature variation. If you look at the zones that are heating, you see they're actually, for the most part, running somewhat higher, and again, their temperatures are somewhere between 76 and maybe 72.5. So temperatures, you can flip back and forth and look. They're not exactly the same in both spaces, but they're not that much different either. But what is different, peculiar about the VRF system is it's just all the systems, all the units that are running heating all day, and about 2/3 and the 1/3 that are running cooling all day. Okay, so what can we say from this? Well, or from just looking at power, why is the ground source heat pump so much better? Well, one reason are the source temperatures. I'll show those on the next slide. If we look at the equipment efficiency, if you look at what the manufacturers rate the equipment are, we try to look at sort of predicted COPs and EER for the air temperatures that are actually occur in Atlanta, and also for the ground loop temperatures that this system's actually seeing. And if you take sort of median values over those those ranges, the ground source heat pump system has higher manufacturer rated efficiencies, higher COP, higher EER. It's not that much higher. I think the numbers, if I remember right, they're definitely discussed in the final report. I think they're in the ASHRAE Journal article. They're better, not enough to explain all the differences, but clearly the ground loop has advantage in terms of source temperature and in terms of equipment efficiency. The thing that we see is this, I'm calling this an apparent control issue, right? Instead of, many times we'll see ground source heat pump system only running, 3 heat pumps on, 4 heat pumps on, but all the VRF units are running. So this is true under moderate load conditions. So however you want to look at that as a control issue, I don't know that it's inherent to VRF systems, but that's what's happening in this system. And then also, what I'm calling, from my perspective, looks like unnecessary simultaneous heating and cooling. Now, I recognize and concede that there's a value judgment here. You might say, oh, well, all those occupants had to have their exact temperature that they adjusted the thermostat to, and it was necessary. But, from my perspective, it looks like the comfort in the 2 spaces that, seems to be similar. And we just, an open plan office space, when we have one unit pouring out cold air, mixing with hot air from the other side, to me that looks unnecessary. But, again, that's a value judgment. That's why I put the question mark afterwards. Okay, there is one other possibility, and that is, well, the loads are different, right? We're going to look at that in the next section. So we'll come back to that question. I put some space here because it's not really an explanation, but we'll look at that. Okay, I'm sorry. I said I would show you the source temperatures. This is the plot for 2 years. The red here is the ambient air. It's what the VRF system is seeing in terms of its source or sink. Right. So of course, as you expect, I think most of you listening will know that it gets hot in Atlanta in the summer, and in the winter it can be rather cold. So the temperatures are, hot in the summer, cold in the winter. But the ground heat exchanger here maintains actually a very narrow band, about 82, 83 degrees maximum, maybe 63 degrees or so minimum. It keeps temperatures relatively uniform over the year. So, okay, with that, we're going to take another short break, and I will be back in just a minute. So, Ted, it's yours.
Okay, thanks again, Jeff. This, again, is your moderator, Ted Clutter, with a quick note to those who may be tuning into our webinar a little late. A reminder that the recording is being made of the webinar, and it will be available on the GEO website shortly after this event. And we're going to have a brief Q&A period following Dr. Spittler's presentation where I will read questions for answer by him and his team. Thanks, Jeff.
Okay, thank you, Ted. Let's see here. It's on. There we go. Okay, so the next question then, the sort of obvious question, well, could this difference in performance be explained by the different loads on the different floors? Now, I told you earlier, well, the lighting plug loads are the same. Occupancy, to me, looks similar, but no, I mean, I don't know exactly. I wasn't there. Maybe everybody on the second floor goes down and sits on the first floor. Seems unlikely. I think most people work at their desks, but, the envelopes are different. And, well, there's more glass facade here, there's a roof here. How do all these things affect the actual loads? So, if you were to look at this, each individual unit, right, and one of the complicating things is we have 14 heat pumps and 22 VRF fan coil units, right? If we want to know how much heating and cooling provided, we really would need to make a measurement on every unit, right? So for all the heat pumps and 14 of the VRF units, they look like this. There's outside air being mixed with return air. That mixes to form the entering air, and then it goes through the unit, then it's discharged to the space. Now, there's 22 VRF units. What do the other ones do? The other ones don't have outside air from the DOAS being introduced into the return air. In those zones, the DOAS air is just being provided via a separate diffuser. So if we want to know the energy consumption, ideally what we would like to do is we measure the airflow rate for each one, measure the temperatures at the inlet and outlet of the unit. Also, for cooling, we'd like to measure the humidities. Okay, now unfortunately, we don't have all that information available. The airflow, let's see, Ted, I'm getting some background noise there. I don't know if everyone's hearing it or not, but in any case, the airflow, we don't have constant instantaneous measurements. What we do have are flow hood measurements, and we know what the airflow was in low stage and high stage, and we know when the units are in low stage and high stage. So using the original flow hood measurements, we can estimate the airflow. Using this though introduced one complication, right? And that is that when we analyzed the data, you could see that there was a clear change in the VRF system operation, change in delta T's and so on in April 2012. We talked to Mike Vaughn at ASHRAE headquarters. It turned out that the VRF systems, their control boards had been changed in April of 2012. So as a result, we did not have, when we did the study, we didn't have measurements. We did later go to the ASHRAE headquarters, but we did not measure all the airflows. So for the rest of this, my presentation, we're more or less going to restrict our comparison for the VRF system to the July 2011 to March 2012, a 9-month period. That's what we can actually estimate cooling loads and heating loads for readily. Okay, so we have the airflows. With that, we have the discharge air temperatures. We have zone air temperature and zone air humidity. And we had to use those to estimate the temperatures entering the unit and the humidities entering the unit. And we used several different approaches. We're limited on time today, so this is described in more detail in both the final report and the second ASHRAE Journal article, which appeared in the December 2014 issue. But if I can try to briefly explain it, first of all, for the ground source heat pump system, there is one, even though we call the whole building a living lab, there's also one room upstairs that is called living lab. That room and the ground source heat pump there are metered, measured. They have more sensors to indicate, so we can find out in more detail what's happening. And so one of the things we found is that the difference between the entering air humidity ratio and the zone humidity ratio is pretty small, whether or not the DOAS system is on. So we have measurements without the DOAS system on and with it on, and this black line is the one-to-one line. Measurements are very close. So we use that as our proxy for the entering air humidity. For the discharge humidity on the ground source heat pump, on that unit we measured the discharge air humidity. It lies very close to this black line here, which is the 78% relative humidity line. So that's what we used for estimating the discharge humidity. Now for the VRF system, we use manufacturer's data to estimate the sensible heat factor for the unit, and then we went and spot checked it, and that's how we estimated the uncertainty. So the uncertainty analysis is a fairly important part of the work. The details are in the second ASHRAE Journal paper, also in the report. And in our uncertainty analysis, we accounted for errors in the sensor. Sensors aren't perfect, so they introduced some error into the measurements. We also accounted for the approximations we had to make, like using the zone humidity to estimate the entering air humidity to the unit. Finally, we also accounted for what we call aggregation. Right, and this is one, I told you, one of the downsides to measuring these systems with distributed units is that they have lots of units, so you need to make lots of measurements. One of the upsides is that because there's lots of units, if the error is random, or to the extent that the error is random, then having 10 units on and some uncertainty for each one, the actual total uncertainty is lower. Much in the same way as if you make 100 measurements of a temperature of something, even though individual measurements have error, by averaging them together, the final error is lower. Okay, so our estimates of the uncertainties are here. For the ground source heat pump system, the uncertainty in cooling is plus 14%, minus 11%. It's not perfectly symmetrical because of the approximations for humidity. Heating is about plus minus 7%, and for VRF, the cooling is plus minus 5%, and the heating is plus minus 4%. Why are we able to do better on the VRF system? It's because the VRF system is always running more units than the ground source heat pump system, so the aggregation actually helps reduce the error. Okay, so first thing we need to look at is how much heating and cooling are we providing. And in this plot, we show the monthly heating provided, monthly cooling provided. The red is the VRF. This is in terms of, I plotted it here in terms of kilowatt hours per square foot. If you'd rather have it in thousands of BTUs per hour or thousands of BTUs per square foot, sorry, we didn't do that. I later totaled it up in terms of thousands of BTUs per square foot, but here it's in kilowatt hours of heating per square foot. You see blue over here, no red, because, again, this is after the control boards were changed and we weren't certain of the airflows. So what do we see? We see here that really the heating is quite a bit higher in the VRF system. So one explanation for those large difference in power consumptions is simply that the VRF system, it is providing more heating, right? So that's part of the explanation on why it's, when you saw the plot, it was 3 times as much. Well, roughly here, the heating's often twice as much, and if you look at a month like March 2012, it might be 8 or 9 times as much. For the monthly cooling, the two systems are much closer. Usually the ground source heat pump is providing more cooling, but in the shoulder seasons, the VRF system is providing more cooling. And it's hard to say absolutely for sure, but to me this appears that this additional cooling provided by the VRF is probably due to the fact that some of the VRF units are actually heating in those months, and doing more heating requires more cooling also. Okay, so those are our estimates, and again, these black error bars here are the uncertainties. And so these uncertainties also give us uncertainty when we calculate the COP. It's just an indicator of how good or how poor we think that the estimate is. Okay, so in total, for this 9-month period from July 2011 through March 2012, the ground source heat pump system is providing 62% less heating and 6% more cooling than the VRF system per square foot. And in terms of totals, I've totaled them up here in terms of thousands of BTUs per square foot. You can see the ground source heat pump system is just a little bit higher. But it's important to note that the VRF system, or the cooling for both systems here, is quite a bit higher than the heating provided. So, if you'd rather, it'd be nice to be more efficient in cooling than in heating. The building has a lot more cooling load than heating load. And again, this is partly, these values here include the impact of the DOAS already. So the DOAS is providing cooling year-round, so there's actually, I guess you could say the difference is even higher than it looks here. For the building as a whole, for our comparison, these are the numbers we're interested in. Okay, so if we take the heating provided every month, and we take the energy consumption every month, we can compute the system heating COP, right? So this includes all the power consumption. For the heat pump system, it's the heat pumps plus the circulating pump plus the losses in the variable speed drive for the circulating pump, plus includes the control boards, includes all the consumption of the ground source heat pump system, and likewise for the VRF system, everything's included here. So the COP here for the ground source heat pump system, it's about 3 for the winter of 2011-2012, and for the ground source heat pump system, for the VRF system, it's about 2 for the winter. So it's, I guess you could say the ground source heat pump system here for heating is about 50% better. Interesting feature, we'll come back to this, not related to the VRF system, simply that from this winter, 2011-2012, to the winter of 2012-2013, the ground source heat pump system COP jumps up almost from 3 to 4, and we'll discuss later why that happens. Okay, well, cooling is even more important. What do we see for cooling? Well, if you look here, the ground source heat pump system has higher, better performance. It varies from month to month how much better it is, but it's better every month. And there is some uncertainty, but even in accounting for the uncertainty, it's always better. So, and it varies some from month to month. And again, an interesting feature, something that I guess it surprised me. When I think about a ground source heat pump, I think, oh, in the winter, the water coming into the ground source heat pump is cold. The cooling efficiency should be really good, and it is. But the system efficiency actually isn't as good in the winter. We'll come back and discuss that in a few minutes. Okay, so another way to look at this, again, system performance is to divide up into bins of outdoor air temperature. We see for the ground source heat pump system, the system EER, including all effects, is a fair amount better than the VRF system. Interestingly, again, another interesting feature which is related to what I just showed you, but the EER is actually improving as the outdoor air temperature gets higher, right? Maybe for the ground source heat pump that's not as surprising, maybe because the ground temperature doesn't change very much, but even for the VRF system, the EER is improving as the outdoor air temperature gets warmer up to a point and then it starts to fall off. Okay, for heating, the COP, the ground source heat pump, it varies some. There's some scatter. There's not that many hours of heating, which is why we get some of the scatter, but it's somewhat better than the VRF system. And interestingly, the COP, at least for the VRF system, for the most part gets better as it gets colder, which again to me was a bit of a surprise. So I called these trends that related to how the performance varies over the year, varies with temperature. They're a little counterintuitive, or at least to me they're counterintuitive. The fact that the ground source heat pump system heating COP goes up from one winter to the next, why is that? For both systems, the EER increases with increasing outdoor air temperature, at least up to a point. And as I'll show you, the ground source heat pump system performance also increases with higher loads. So we're going to look at some of these things as sort of our last topic. So the ground source heat pump system EER is better in hot months. When you plot it versus the total cooling provided, right, you can see very clearly that there's a strong trend. It's fairly flat in the hotter months with higher loads, and then it falls off. Okay, that is related to an important feature of this system. This system has a central pump. It actually has two central pumps, but operation, just 1 week it'll use one pump, the other week it'll use another pump. It has variable speed control on the pump, so as the load on the system falls off, or specifically as the number of heat pumps that are on falls off, the pressure, well, each heat pump has its own two-way valve, so when the compressor goes off, the valve shuts. That would, if nothing else happened with the pump, that would raise the delta P across the heat pumps, so basically the pump slows down to control the pressure. And this system also has another feature. The building energy management system actually turns off the circulating pump if there's no load. So at night, it's often the circulating pump's off. So that's probably the best possible scenario, but nevertheless, the actual energy usage depends on this differential set point. And some years ago, around between 2011, between the first winter of 2011-2012 and the second winter of 2012-2013, several of us were at the headquarters building, and a well-known engineer in the ground source heat pump area, Kirk Mesker, looked at this setting because it was actually you could see what it was on the from the pumping closet. He noticed it was 20 psi, and he said, "Oh, that's too high." So he got ASHRAE to set it down from 20 to 8, and that considerably lowered the pumping power. Now, when we were there in May of 2013, I think it was May of 2014, we actually changed the set point on the system and made a few measurements. We don't have a very complete set, and we don't have an exact match to what it was that day. We just got measurements at 8 and 15, but if this is the kilowatts being used by the pump and the pump control versus the loop flow rate, and you can see there's quite a large difference here going from 8 to 15, and at 20 we would expect the power consumption to be even higher. So the real reason why the COP improved was that the set point was changed and made the system more efficient. This, in a way, is also the explanation for the other features. Why does the COP improve from the first year to the second year? Right, because it was changed. Why are the trends counterintuitive? Why are the trends counterintuitive? Why specifically does the EER go up as it gets hotter, or up with higher temperature? Well, for the ground source heat pump system, there is true that entering fluid temperature doesn't correspond directly to the outdoor air temperature, but nevertheless, it's the trend's fairly uniform. It keeps going up. The real reason is that as it gets hotter outside, We have a higher runtime fractions for the heat pumps, and that means that for any per unit of cooling provided, or in the winter as it gets colder per unit of heating provided, there's less pumping energy, and the parasitic losses, there's less control board and standby power for the pump. There's less of that type of energy used per unit of cooling or heating provided. So to my way of thinking, this highlights the need to be very careful about how we design pumping systems for ground source heat pump systems. Now, we see similar trends in the VRF system, and I should emphasize, I put here, we speculate, right? We did not make internal measurements of the refrigerant flow rates and pressure states and so on. It's simply that this simultaneous heating cooling is not as efficient as might be imagined. So that as we get to lower outdoor, say we go from hot outdoor air temperatures to more moderate temperatures, we get more simultaneous heating and cooling. I think that changes the inside performance or operation of the system, may change what pressures it can be run at, and I suspect that affects the efficiency. But this is speculation on my part. I don't have a complete bulletproof explanation. So, to wrap up then, for this building, for the time period we studied, the ground source heat pump system significantly outperforms the VRF system. If we look at the 9-month period where we could calculate the COP and the EERs, the COP is about 50% better, actually a little better than 50% better for the ground source heat pump than the VRF. The cooling system EER is something like 60%, 60-some% better, 8.5 to 14.5. So the performance overall, even with everything considered, pumping system, heat pumps, everything, the ground source heat pump system significantly outperforms the VRF system. Why is that? Well, again, the ground source heat pump has more favorable source temperatures. The heat pump unit efficiency is higher than the VRF efficiency over the actual range of operation. And the VRF controls lead to what look to me to be unnecessary heating and cooling. The unnecessary heating and cooling was included in the COP and EER calculation, so it's not, in one sense that's included, so it's not responsible for the COP and EER, except to the degree that perhaps simultaneous heating and cooling are impairing the efficiency. So I'd like to wrap up with a thank you to GEO, funding the research, and Southern Company for funding the research, and also Southern Company when we got time to go make our site visit, and I wanted to measure the power consumption of the circulating pump. And actually we measured power consumption of some of the heat pumps. I got a little bit nervous about whether I was going to go to the building electrical panels and actually make hookups myself. And thankfully, the Southern Company provided a power engineer, so thank you, Chris. Also, the U.S.-China Clean Energy Research Center for Building Energy Efficiency supported some of Dr. Liu's time at Oak Ridge. I'd like to thank ASHRAE and specifically Mike Vaughn, who helped us a lot with getting access to the data and also helping us with our site visit, spending the day giving us a kind of an extended technical tour of the building. So thanks, Mike. And but of course, as Doug emphasized at the beginning, ASHRAE is not responsible for the results, and they're not endorsing any products here. And then finally, I'd like to thank Daikin, Climate Master, and Train, all of whom donated equipment to ASHRAE. I appreciate that. They donated knowing that people like me would come along later and measure performance. So it takes a certain amount of guts. So thank you very much.
And thank you, Jeff, for your presentation.
I think you have it now.
Yeah, thanks very much for your presentation, Jeff. We now come to the Q&A part of our webinar, and Dr. Spittler will be joined by his research team, Laura Southard and Xiaobing Liu. We've got really great participation today. On my panel, I've showed as high as nearly 900 participants in our audience. And we've got a lot of questions. So I'm showing 59 questions at this point, so we'll do the best we can with them in the short time we have left. And we might, after the webinar, answer some of them in writing and put them up on our GEO website. But before we get started on the questions from the audience, I have at least one. Jeff, would you mind elaborating a little on the independent and peer-reviewed nature of your work when you were comparing the heating and cooling systems at the ASHRAE building?
I can say a few words about that. So we, first of all, we did the work, I'd say, very independently. To be honest, when I started the study, I really expected we'd find, I thought we'd find more of an explanation of why the ground source heat pump system seemed to be outperforming the VRF system. That was before we made any estimates of the heating and cooling being provided. I thought maybe that would provide more of an explanation, but we found what we found, and that's what's presented. In terms of peer review, we published 2 articles in the ASHRAE journal, and they were, well, I've published, 100-some technical papers, so I have lots of experience with review processes. I know the difference between a thorough review and a not thorough review. And these were very thorough reviews, very sort of well-done reviews, and we had to address a number of things, including revisiting actually how we did the uncertainty analysis. We actually went back to the site a second time to make some more measurements to confirm things. So they were thoroughly peer-reviewed, and that's what's in the ASHRAE Journal article. And actually, we redrafted parts of the final report. Well, I think it was an improvement in how the uncertainty analysis was done, how we estimated the humidities, and so on as a result of the peer review. So I hope that answers your question, Ted.
Yeah, thanks a lot, Jeff. We'll get to the audience questions. As I say, there are very many of them. Scrolling through them, first I have from I hope I'm pronouncing his name correctly, Thomas Pikunka, asking why is the DOAS airflow higher on the first floor when the occupancy density for the first floor is lower? Is the DOAS higher airflow on the first floor due to the VRF system ventilation requirement?
That's a very good question, and here's it's one I actually don't know completely the answer to. So after I take a swing at it, if Laura would like to jump in, that's fine. I don't think we know why. My recollection is that the airflows are relatively constant all the time, so it's not a question of it being controlled by like a CO2 sensor. I suspect, but again, this is speculation, that it was probably sized with some maximum, or probably adjusted with some maximum occupancy on the first floor, including maybe a completely full learning center. But it never changes over the year. At least that's my recollection. So Laura, feel free to correct me if I've misspoken.
Yes, I would agree that I think the original airflows from the DOAS were set. The design flow rates were based on a fully occupied learning center, so that would have been more people on the first floor, even though that's not typically the case on an ordinary day. And then while there are CO2 sensors that adjust the DOAS flow from one zone to another, there doesn't seem to be a real good way for them to readjust the split between how much goes to the 2 separate floors.
So that's it, Ted.
Pretty well answered that question. As I say, there's a lot of them here. It's hard to make a good choice, but interesting perhaps is what kind of refrigerant is being used with the VRF. Did you have privy to that information? Or just standard refrigerant, or?
We might have, but I don't remember. Laura or Xiaobing, do you remember? I mean, I'll just say. Go ahead.
R14A. That is my recollection.
Okay.
Yes, that's correct.
Another question here from Rob Buchanan. What steps were taken to separate the building envelopes within the building to ensure that the VRF and the geothermal system were not competing with each other? How separate were the envelopes, both in terms of building tightness and insulation levels? To take loads slightly out of the equation, can you compare the average COP and EER between the system over the 2-year period?
Yeah, so let me take that question in slightly reverse order. We can't do it over the entire 2-year period, but The basis of all the COP and ER comparisons that we showed for the 9-month period, those are only based on what the systems are providing. Okay, so any differences in the envelopes are, as it were, factored in. So in terms of could they be competing, it's possible. I don't think the two systems would compete with each other very much, but I'll describe that in a second. But in terms of the COP and ER comparison, that includes if there are any envelope interactions, they would be included. Now, to address the question, yes, there could be some heat transfer from one floor to the next, but given the fact that we have a suspended ceiling, concrete slab, between the two floors, and the air temperatures, as you saw, were within a few degrees Fahrenheit of each other, I expect there to be very little conduction heat transfer. And yes, there may be some airflow, but the doors between the second floor and first floor are shut. So the stairways have doors that are ordinarily closed. So I don't expect there to be a lot of airflow, but of course it's possible there's some small effect on the envelope loads. So I hope that answers the question. Thanks, Ted.
Sure. Why is this is Kathleen Dorsey asking, why is the ground loop temperature band so narrow? Is the ground loop larger than normal for the given annual and peak loads?
Okay, that's a good question because I think many ground source heat pump systems would be designed, probably would have a wider temperature band than what we see. And I wasn't privy to all the design calculations, and I didn't go back and ask to see. So I speculate on this, but my speculation is that you could say either the ground loop is oversized, or perhaps it's oversized for the system with the DOAS taking as much of the load as it does. But when I say oversized, well, there's estimates of how much heating and how much cooling were being used, or would be needed to be provided by the ground source heat pump system, and if those estimates were overly conservative, that will lead to the sort of situation that we see here. Having said that, it would be quite interesting if we had some kind of statistical basis to know how much typical system varies from the design due to the difference in loads. But that's my answer. It involves some speculation. So,
Sure.
Ted, could you give me the next question?
You bet. I hope I'm pronouncing the name correctly again, from Mike McKemmehy. He says, by your own numbers, there is a 73% more outside air on average going to the first floor. Since the DOAS is operated based on actual CO2 levels, is not that a direct indication that the people density on the first floor is considerably higher than on the second floor?
Well, this is sort of similar to the question asked earlier. It doesn't appear to be. It's always the ratio. The ratio is always the same between the two floors, and the airflow rates to the two floors are about the same. So it's not, as far as I can tell, it's not what you would think of as a demand-controlled ventilation system, where the actual outdoor airflow corresponds to the CO2 levels. So,
Daniel Tyson asks if the.
Ted.
I'm sorry.
Next question.
Daniel Tyson asks.
Go ahead with the next question.
Daniel Tyson asks, does the VRF system have heat recovery?
Yes, it is a heat recovery type of VRF system.
And Pedro Gomez asks, what is the average heating DAT for the VRF system into the spaces? Could stratification be driving the higher energy use for the VRF system in heating mode?
He's asking I'm sorry, Ted, was he asking the average supply or discharge air temperature? Was that what the question is?
DAT. the average heating of DAT?
Laura, do you have an idea what the average values were?
What was the question one more time?
What is the average?
Well, he was asking what is the average discharge air temperature
the VRF system into the spaces? Could stratification be driving the high energy use for the VRF system in heating mode?
Well, the discharge air temperatures actually varied a fair amount. In heating mode, when a VRF fan coil unit would first turn on, the air temperatures would be a little over 100 degrees at the discharge, but then as it continued to run, they would drop off gradually. I don't really know whether stratification was involved in that.
Okay.
I don't really have an answer for how stratification might have influenced the results. I don't think you'd find the building was very stratified, but perhaps the questioner had something else in mind. So perhaps we should move on to the next question.
Sure. From Daryl Pater, do you have any idea why the controls conflicted on the VRF and not with the geothermal heat pump system?
Yeah, I would attribute it to the fact that the ground source heat pump system had a dual set point, and that would be part of it, and then the other part, may have to do with internally how the VRF system is controlled. It seems to have you could say, a predisposition to run all the time. But I would say, first of all, the dual set point is less likely to lead to simultaneous heating and cooling. We had very few hours when there was simultaneous heating and cooling in the ground source heat pump system.
From Greg Day asking, how did you correlate difference between single point control at 72 to dual set point control heating at 68 and cooling at 74?
Yeah, we didn't attempt to make a correlation. I mean, if you saw the actual temperatures for like the day in April, they varied some, and there was not, because it's not really 68, 74, it's 68 plus minus 3, or 74 plus minus 3, and it's not single set point 72, it's 72 plus minus 3. The temperatures are fairly similar, and having worked in load calculations a long time, I think if you looked at the average temperatures and did a detailed analysis, you'd find that had a very small difference on the loads. But nevertheless, the difference in loads is factored into the COP and EER calculations. So it may have some influence on what the loads are, but again, my opinion is it's pretty small. So next question, Ted.
Sure. From Mahid Shafiq, did the team run building load calculations for cooling and heating? I believe you explained all that pretty well.
Well, no, I'm laughing because, in fact, we ran detailed energy analysis with eQuest, and and we spent some time calibrating the results and so on. But in the end, I decided it was that the results were kind of interesting, but they didn't really add to the study because it was difficult to quantify the uncertainty. So actually, in the end, we dropped all that discussion because I think maybe it provides some insight on why the loads were, but why they were the way they were. But in the end, you also then end up with a lot more interesting questions like well, how much of the load difference was due to the blinds, and we estimated the blinds were on average 35% open. Well, how accurate is that? So on. So I felt like in the end it just introduced more questions than it answered, and really didn't provide such useful information. So we did it, but we dropped it from the final report. So,
Jeff, a lot of the questions are turning to whether or not you did a life cycle cost analysis, the differences in cost between systems. Perhaps you can elaborate that, about what your study actually focused on.
Right. Well, it's also a very interesting question, and I'll tell you exactly what we did. We never intended to do life cycle cost analysis. I did at one time plan to at least compare the initial costs, and we got ASHRAE at one time asked the manufacturers to compare to value their donations. So ClimateMaster donated the ground source heat pumps and the boreholes, the ground heat exchanger. And Daikin donated the VRF equipment, but not the installation. And ClimateMaster, as I understand, didn't donate the ducting and installation of heat pumps, but just the ground heat exchanger. So the two companies both gave values. The Daikin valued the VRF equipment somewhat higher than ClimateMaster valued the ground source heat pumps and the boreholes, which I thought was very interesting, but it was also hard to know from the data we were getting exactly what the manufacturers, if they were really doing if we could really do an apples-to-apples comparison. And at least one practicing consulting engineer in Atlanta, I discussed this with, he was somewhat skeptical of the two numbers as really, being an apples-to-apples comparison. So that's why in the end, we didn't present those values because I couldn't be sure of what they were. It's hard to know if the ground source heat pump system really would have been cheaper to install or not. And given the fact that those numbers were, it was hard for us to know exactly for sure if even they intended for them to be the same basis. We left that out. So good question, but that's the answer. So next question, Ted.
Okay, from our friend Jay Egg in Florida, he asks, if this is cooling dominated, wouldn't you expect the ground to progressively warm, possibly leading to at least part of the improved COP and heating in year 2?
Yeah, it's not. Let's see. We looked at this for we looked at the ground heat exchanger for the full period. It's not. I guess you could say the ground heat exchanger is large enough that we don't really see too much temperature rise. The actual yeah, that's a good question. But the loads. I guess they're not as unbalanced as it looks, and it's a fairly large, oversized system, so we don't really see much temperature rise.
Okay.
Interesting. So, okay, let's go on to the next question.
Yeah, that's, I think, somewhat related and kind of speculative, but I'll ask the question anyway for Pam Jenny. How would you expect the two systems' comparable efficiencies to change as you move north from a cooling-dominant climate to a heating-dominant climate?
Well, again, it's hard to know absolutely for sure, but if you look at the plots where we plotted the COP and EER versus temperature, the VRF system is, or the ground source heat pump system has about 50% higher COP and maybe 65, 70%, something like that, higher EER. But it changes with temperature, so it might be that the comparison might, as we got more cooling loads, it might be that the ground source heat pump system wouldn't outperform as much. But it's difficult to say, and I think really without having, it would be much better to get another test case than rely on extrapolating the results.
That's an interesting question I'm not sure you addressed, but you may have gotten a feel for while you were doing your study for the past several months. How did occupant satisfaction differ between the floors, or was that even talked about by people at ASHRAE?
Here's an interesting, another interesting thing is ASHRAE actually did like an occupant satisfaction survey, but they never broke it down by occupants of second floor versus first floor. So I think that's something we have to leave for a future survey. In terms of when we talked to people there, we got absolutely no sense that anyone was unhappy with thermal comfort on either floor. Nobody approached us and said, oh, the second floor is really bad or the first floor is really bad. So hard for me to really, it would just be speculation, but I think it would probably be interesting to see if there was really an advantage to the VRF thermal comfort by having the narrower temperature control. Certainly if you look at the day that we were there, the temperatures over the whole system varied as much with the VRF as it did with the ground source heat pump system. So that's my attempted answer, Ted. Why don't you give me the next question?
Let's see if I can find you a good one here. Jake Andrews is wondering if you can discuss potential initial costs of the systems. Again, it's a cost question. But did you get a feel for the well drilling cost versus exterior units being installed, and any kind of information on payback at all from ASHRAE? Did they discuss that with you at all? Jeff, are you there?
Ted, are you there?
Yes, can you hear me?
I am sorry. When you were just introducing the question, all of a sudden I got, that.
Okay, can you hear me now?
I can hear you now, so go ahead with the question.
I'm not sure what happened there. Excuse us, folks. This was a question talking about cost analysis, and if you had any idea of the cost differentiation between drilling the bore field and installing the units on the roof and so forth. Was that addressed at all by ASHRAE? Did you get any information about that at all?
Right. Yeah, maybe I should mention I had the information about that I discussed earlier about the heat pumps and the ground heat exchanger cost. I didn't. Again, I said I didn't know if the manufacturers were really giving it on the same basis, or not. And no, we didn't have any information about, say, the cost of running all the refrigerant piping on the roof, how that compared to running the water piping. So that was really another reason for not trying to cover that in the study.
Right. So I think you've explained that pretty well. This really was not a cost study. It was an efficiency study based on the equipment, the technologies. This is a technical question by David Wilson. Does a VRF compressor reduce the startup current spike compared to a normal compressor? Do you have any information on that?
I don't. So that's and for the most part, most of our measurements were longer intervals in the startup current spike. So I really don't have any answer for that, Ted.
Okay. The majority of the questions, as I say, really ask the cost question. I think you've answered that as well as you can, Jeff. And many folks have asked if they're going to be able to download slides and if they're going to be able to see the presentation. And as I've noted before, this whole presentation will be available on our website. So. Thanks again, Jeff. Great presentation. And at this point in time, I think that Doug Dougherty has a few follow-up comments. Doug?
Thanks, Ted. To all that are still on the call and joined us today for this webinar, I hope you found it of value. If you're a member of GEO, this is one of the many values provided through membership. And if you're not a member of GEO, we would hope that you would consider joining GEO for these types of benefits. It's only through the dues paid for membership to GEO that we were able to help improve the market for geothermal heat pumps, both from an advocacy standpoint and from a research standpoint. So I'd ask you, if you're not a member, to sign up and join GEO, and you can do that at our website, which is shown on the slide for you. Again, thanks to Dr. Spidler and his research team, and to Ted for moderating this, and I hope everyone has a healthy and prosperous new year.
Okay, Doug, thanks a lot. I'll say it again that this webinar has been recorded and will be posted on the GEO website soon. And there you can also access the full final report of the study on geothermal heat pumps versus variable refrigerant flow systems at the ASHRAE International Headquarters building in Atlanta. We hope you enjoyed the webinar. With Doug, I want to thank our research team for taking the time today to spend with you to explain their study and how they went about it and how their findings correlated with the building. And I want to thank everyone who helped us get the word out about our webinar. Many different organizations and state associations and ICSPA helped us spread the word, and as well as our member companies. And I'd like to thank all of you for your attendance. Repeating what Doug said, I hope all of you have a healthy and prosperous 2015.